Welcome back. Last time we left off, we were talking about the the different cells of the retina layer, the rods and the cones, and specifically how these are the cells that are responsible for helping give us our vision, being able to understand shapes and to see color and detail. And so today, what we're going to be focusing on is specifically how these cells are taking what they see on the back of this retinal wall here, and how our brains are then processing it as a picture or an image. And so what we're going to be looking at is uh, how this image gets relayed, and specifically how this image is even created. Because the way our eyes work are simply like a camera, and you can think of them like a camera, taking in light source, projecting an image, and then our brains are going to process what it sees. Now, they're going to process what they see pretty much everywhere in the eye except for this tiny little spot right here. And that's what we're going to start off on. So we're at number 4 in our notes, the structure of the eye, the sensory layer. So again, the signal is going to leave the retina and it's going to travel through the brain or to the brain through the optic nerve. Now, where this optic nerve is located on the eye, you can't have any rods or cones in that location of the retina because, again, you need a place for this nerve to connect. And so it creates what we call a blind spot. Now, you might think of a blind spot for like when you're driving your car, somewhere you can't see outside the mirrors or the window. And this is very similar in the sense of it's actually a blind spot in our own eyes. You see where it says that optic disc, that's this location right here. And at that location, we go here, you notice there's no rods or cones, and so you're not going to be able to produce an image if your eye is seeing something here. Now, how many eyes do we have? I would hope you would say 2. And if both of those eyes are working, our one eye compensates for the other one's blind spot, because the blind spots are going to be a little bit different for each eye. And so we generally don't notice this blind spot unless we're looking with just one eye. And so that's what this says down here. That's what this little index card trick thing is. And I'm going to show you what that is right here. All right, so what I'm about to show you is what's called the index card trick. Now, what you need is an index card or just any piece of paper about this size. And what you're going to do is on one end, you're going to put a big red dot. And on the other end, you're going to put like a big red X, or it doesn't matter the color, but like a big X or a cross. And it should look something like that. All right. So what you're going to do is you're going to take this and make sure I have the X to my right. All right. And I'm going to close my right eye now. All right. So my right eye is closed. And I'm going to focus just on the X. I can see that dot there, but I'm just focusing on the X. And I'm going to slowly start to pull it towards me, just focusing on the X with my left eye. And eventually I should get to a point where I can no longer see that dot and it will just appear white, which is right about, it's a little fuzzy, it's about right in there for me. And so what's happening is as I'm looking at that X, that little dot is disappearing. It's still there on the paper, but what my brain tells me is that it's not there and it's white. And what's going on is because of our optic nerve, where that nerve ending is at on our eyes there is no room for the retina. So there's no rods or cones. And so that's what we call our blind spot. It's what's known as the optic disc. And so you can do the same experiment with your other eye. It's hard for me to find my blind spot on my left eye, but I can find it on my right eye a lot easier. So what you do, again, close your left eye this time, and my index card is still facing the same way, so my dot is going to be on the left. I close my left eye, and I use my right eye to focus on the dot this time. And so I'm going to bring it closer and closer and closer, and eventually I should start to see right there. the X has disappeared. If I look there with my right eye, still focusing on the dot, it just looks like it's gone. And so you can try this trick at home. And if these instructions are still a little confusing to you, what you can do is I put a link in the description to do this for yourself. So I hope this helps. And now back to the lecture. All right, so moving on from there, again, the reason when you would put that index card up to your face and at a certain level you couldn't see either the X or the spot was simply because what was happening was your eye was focusing on it, and where that image was being projected was right here at the optic disc. And of course, if that image is being projected there at the optic disc where there's no retinas or where there's no rods or cones, you're not going to be able to produce an image. And so your eye compensates for that, and if it can't see what's there, it's going to assume that that portion of the image is like everything else around it. And so that's why everything turned white and it looked like that dot or the X just disappeared, because the rest of the eye was trying to compensate for that. And it was saying, well, the rest of the image around it looks like it's just blank, so we're just going to leave that blank. And that's what's happening with our blind spot. Now, again, we have two eyes, so generally that's not a problem for us. But let's say you're legally blind in one eye, or you do lose an eye. Occasionally you might see that blind spot from time to time, but in most cases your eye is still going to try and compensate for it in one way or another. Alright, so before we move on any further, I want you guys, yes, I know you love Crash Course, but I want you guys to go ahead, pause the video, and watch this video from Crash Course. What it's going to do, it's kind of going to give an overview of the layers of the eye, about the first minute, from about 2.5 minutes to 4 minutes. That's basically a review of the eye layers. But what it's really going to talk about is what our vision is. Like, what is vision? And it's going to discuss how we basically are taking in rays or waves of light, and how that light is then getting bounced off of certain things and then reprojected on the back of our eye to make a picture. And so he's going to kind of talk about that, give a basic overview, and around minute 6, he's going to start talking about the rods and the cones and how they work together to really perceive that picture, and how even sometimes our eyes can be tricked. And again, this is just going to be a basic overview of this video. It's going to basically explain what we're about to talk about. So go ahead, pause this, and then once you're done with the video, we're going to break it down together in our notes. Alright, so I'm assuming that you went and you watched the video, and so we're just going to be moving on from there now. Alright, so our lens. So of course our lens, that's the part, just like a camera, it's what's going to be bending that light source and then projecting the image on the back of our eye. Again, there's no space in your notes for this, but by the lens or lenses, I want you to put this: bends light to produce image. Again, what our lens is doing, it's going to bend light to produce an image. Now, it's not just the lens in our eye that's going to do that. That's any lens that you look through. Ours just happens to be what's known as a biconvex lens. And it says crystal-like structure simply because that's what it is. Now, it kind of has like a hard jelly consistency, you could say. And it's kind of rubbery and pliable in the sense that it can move. And we're going to see later on why that movement is important for helping us focus on certain pictures. But for now, what I want you to have down is that what lenses do is they bend light to help produce a picture. Alright? So again, it's going to be held in place by these little suspensory ligaments in the ciliary bodies. And what's going to happen is if we're trying to focus on a picture, sometimes this might contract and pull, and it's going to change the shape of our lens. And as that lens shape changes, so will the way that light gets bent. Now, some of this might seem a little confusing, trying to figure out what in the world is Mr. Eversole talking about, light bending, all this. And so that's why we're going to look to Bill Nye in just a second to help us with that. But before we do, what is this? All right, just take a second. What do you think it is? If you said a cataract, you would be correct. And so what happens is, generally, again, our lenses are normally clear. It's almost like a crystal clear structure when we're born, but as we get older, they start to get opaque. In other words, they get foggy, and this is just something that happens with age, but it can be, the process could be sped up with certain factors like diabetes or just being exposed to intense light and even heavy smoking. All these different things, these chemicals and whatnot, can affect our lens and they can start to mess with our vision. Now, there can be surgeries to remove cataracts or to help clear the lens up, but eventually this just does happen with age, and eventually it can lead to blindness. Not always. You're not always going to develop cataracts, but this can occur. All right, so before we move on, again, I just want to reiterate what in the world our lenses do. They help us to bend light to produce a picture. And Bill Nye is going to help us explain this. So again, I want you to pause the video right here. I want you to go to this link or follow this video. If you have the notes downloaded, the Google Slides, go ahead, click on this video. Watch this one real quick. He's going to explain how our lenses work, and then we can move on. All right? So I'm assuming that you went and watched the video. And again, he explained how we have different types of lenses. There are concave and convex lenses. Convex lenses are generally going to make smaller images, and they're going to produce, in our case, what's known as a real image. We're going to see that later on. But ours is, again, a biconvex lens, and it's this lens that is going to divide our eye into two different segments. And so those two different segments or chambers are going to be the anterior and the posterior segment. All right. The anterior segment is going to be filled with a humor. And again, when we say humor, we're not talking about something funny. We're talking about like a liquid. That's what the term humor means. And so the anterior segment is filled with an aqueous humor, or aqueous, however you want to pronounce that. Either way, know that when we're talking about the anterior, in other words, the front of our eye right here, this segment is filled with a watery-like solution. And that's going to help, again, it's going to be very clear. It's going to help with focusing or just protecting our eye, giving it that shape that it needs to. And that's, in reality, all these humors are doing in our eye. This is what helps keep our eyeballs inflated, you could say. It's the different humors that we have. The anterior is going to be aqueous, and then our posterior segment is going to be the vitreous humor. And it says gel-like. In other words, I'm not sure if any of you guys have ever done anything with like water crystals, or probably you're more familiar with them as Orbeez. All right, your vitreous humor kind of has that consistency to it. They're kind of like Orbeez, and again, what's happening is this fluid in here helps basically keep our eyeballs inflated. And if they're not inflated properly, then we can't produce the correct image on the back of our retinas. And so it's important that we have just the right amount. Too much can actually cause damage, and too little can cause us to have poor eyesight as well. All right, so again, this is just a closer up view showing you the vitreous humor that's going to be in that posterior segment, and then the aqueous humor that's going to be in the anterior. And the way that you can remember this, again, mnemonic device, anterior starts with what? An A. Aqueous starts with what? An A. So that's the easiest way to remember. Aqueous in the anterior, and then just vitreous in the posterior. All right, so for our eyes to be able to focus on something, we need to be at least 20 feet away, or at least that's what our eyes are set for without accommodations. In other words, when the lens is at its normal size, whatever it's supposed to be, uh, we should be seeing that crystal clear just about at about 20 feet away. Remember what's happening. Our lens is going to be bending that light. And as it bends the light and all those rays meet together, where they converge together, that's where we produce that image. That image should be being produced at the very back at that focal point on our eyeball, on our retina. And so what's happening is, again, let's say we're standing 20 feet away and we can see something perfectly fine. All right, then that would be what we consider 20/20 vision. In other words, somebody who has standard vision can see something at 20 feet away. That's where that comes from. Now, if we have 20/20 vision, uh, that means that, let's say we get closer to the object. Well, naturally, it's not going to be in focus, but our eyes can do what's called accommodation. All right, in other words, those ciliary bodies, those suspensory ligaments, they're going to be moving our lens. They're going to be shaping it. They're going to basically give it a different shape so that when the lens bends that light, it's still going to focus properly. So again, let's say you have 20/20 vision and you stand 10 feet away from the object and you can focus on it fine. All right, your eye still had to do some accommodation in order for that to work. Again, when you think of accommodation, think of a camera. Even on your cell phone, if you put your camera up close to something, it's going to be kind of blurry for a second, but then it's going to slowly start to focus. And then you take it away and it's going to have to focus again. Your camera is having to do accommodations. Likewise, our eye, just like a camera, is going to have to do the same thing. All right, and so again, this is just showing you that normal focal point. We always want our image to be focused here. That's going to be the main point, because again, look, we have those light rays coming in, they're hit by that biconvex lens, and so all those light rays start to get bent, and where all those light rays bend and meet, this is where we produce what's known as a real image, right at that focal point. Now, that focal point is important. It should be right here at the back of the eye. If it's back here, in other words, where when these light rays hit the back of our eye, it's not going to come together, it's going to be blurry. If it comes a little too early, again, we're going to see some of these things, and that's what you guys probably read in your articles today about farsighted and nearsighted, and we're going to look at that in a second. And so again, you can see here though, look, our lens has changed its shape because the source has come closer to us, and so we have to accommodate for that. That way we can still see it in focus. All right, so again, what's going to be happening is as we start to focus on these things, yes, our eyes do see it upside down, because what we're producing on the back of our retina is what's known as a real image. All right, and this real image is going to be something that, again, it's going to be reversed from left to right. It's going to be upside down, and it's going to be smaller than the actual object. All right, in other words, you might be looking at, instead of a giant J, let's say you're looking at a tree. All right, that tree, the image that you produce on your eye is definitely going to be smaller than what you see here. Now, again, some of you guys might be confused. Well, what other image is there besides a real image? Well, this goes into physics, and we're not really going to go into too much detail about this. I'll let Bill Nye explain it in just a second a little bit better. But what's going on is you either have a real image or a virtual image. And the best example of a virtual image is what you see in a mirror, that reflection. Again, the image that you see in the mirror, it's the same size. It is going to be reversed, but nonetheless, it's still going to be that same size. And so that would be what we call a virtual image. But remember, our eyes are making a real image. All right? So, again, what I want you to do is this one's not as long. Just go ahead, pause the video, watch this little clip about Bill Nye, and he's going to be talking about how our eyes are producing that image and what a real image is. All right? So I'm assuming that you stopped the video and you went and watched this one, and now you're back to finish our notes. So the last things that we're going to be talking about today are some defects and imbalances in the eye. All right? This right here is just kind of showing you our peripheral view and how our right eye and our left eye see. This is showing you from the bottom here. All right? We're going to look at the eye reflexes. In other words, how do our eyes work? In other words, when something's coming towards us and we flinch, or somebody shines a bright light in your eyes, what's happening? Are you doing any of that? Like, are you responding to make your eyes, your pupils get smaller so they don't take in that light? Are you responding to make your pupils larger so they can take in light? And the short answer is no, you're not doing it. These are all reflexes. In other words, it's being controlled by that autonomic nervous system. And so what's happening is, again, you go into a bright room, your eyes are going to, the pupil is going to get smaller because it doesn't need to take in as much light to produce the image. But if you go somewhere where it's really dark, your pupil is going to need to enlarge so it can take in as much light as possible. That way it doesn't appear too dark and you can start to make out images and things like that. Another thing that you can think about is creatures that are nocturnal. Normally their pupils are actually slanted vertically. In other words, they're not side to side, but they're horizontal. They're vertical, going up and down, and that's because they can open them even wider. Then that way they can get a lot of light in. And again, they're not controlling that. This is all automatic. All right. And so, likewise, even when we look at something up close, those accommodations that we talked about earlier, where our lens is going to be bending so we can focus on things, we're not doing that, or at least we're not thinking about doing it. Our brains automatically know we need to focus. And so again, it's that autofocus on your camera, only it's with your eyes. All right. However, sometimes our eyes have a hard time doing this, and this is generally because we have different shapes of our eyes. Now, these two diagrams here should look familiar if you read the article about being farsighted or nearsighted. I happen to be in the category down here with hyperopic eyes. I am farsighted. And so again, what's happening with these different conditions, if you have a normal eye, if your eye is emmetropic, what that means is that, you have the right distance, your cornea is okay, and your eye is just the right size so that when all those light waves intersect and meet, they meet at the focal plane. That's what this dotted line represents. In other words, this should be where the image is being produced. All right. However, what our eyes are going to process is always the back of the retina, whether or not it's at the true focal plane or not. So what's going on here with this person who might be nearsighted, they're actually going to have an eyeball that's larger than usual. And so this vitreous humor is going to enlarge this area. And see right here, that should be where you're focused on the object. However, if somebody who has myopic vision is looking at something, let's say 20 feet away, like this person, all right, this person can see something 20 feet away absolutely fine. This person, all right, it's actually going to be fuzzy for them. And that's what this is right here. See where all these light waves are no longer together? That would be a blurred image. And so to correct that, that's why you have to have a concave lens. So what's going to happen is, again, all these lines are representing the light that comes through. This concave lens, it bends that light before it even gets to our lens. And so then when your lens is able to bend that light, see where that focal point is at? Right where it should be. And so that's what's going on there. Now me, my eyes are small. I have the small eyes. I'm farsighted. What this means is, again, let's assume that this person, all these people are looking at something 20 feet away. This person can see it absolutely fine. This person, it's fuzzy. Somebody who's farsighted, do you think it's going to be fuzzy too? And the correct answer is yes. However, for this person, instead of getting closer, having to get closer to see the image, they actually have to back away. See where their focal point is actually farther away outside the eyeball, so this person would have to back away. In other words, if you're farsighted, you can see things that are far away pretty good, but when somebody puts something right in your face or you're looking at a computer screen, your eyes are really having to strain. And that's how you can also get lots of headaches. It's the same if you're nearsighted, in the sense that your eyes are going to be straining if you don't have these corrective lenses. And again, if you're farsighted, you're going to need a convex lens. Notice this one's like a biconvex lens, very similar to what's actually in our eye. Because again, the eyeball is smaller, and so it needs to bend these rays before it even gets to our lens, and then that lens is going to bend them a little bit more. So again, it focuses right where it should be. So if you're somebody like me who has glasses but doesn't wear them like they should, you're probably going to be getting some headaches when you're doing things like watching this video or just your general homework and things like that, or even reading. For example, I should be wearing my glasses right now, but I'm not. And my eyes are straining just having to look at my computer screen right now. And so again, when you get a prescription for glasses, they're important. All right. Astigmatism. I got one of these too. And what happens with astigmatism is usually there's an unequal curvature of either the cornea or the lens. In other words, what that means is, remember, our lens is bending light. The cornea, again, that cornea is curved, it's going to be bending some light too. And if that cornea itself is bent, then what's going to be happening is that light gets bent before it even gets to the lens, and then when it does get to the lens, you're not going to be able to focus right, and that image is going to be blurry. And so that's what's going on with astigmatism. And so when you have astigmatism and you're farsighted, you really should be wearing glasses, or at least having contacts. So when you see me without my glasses, you should be like, Mr. Arso, where's your glasses? But that's for another day. All right, so last but not least, a few different things that can happen with our eyes. These are things that maybe some of you might have talked about night blindness before, or I know we've all heard of color blindness, especially if we talked about it last year in biology with sex-linked traits. But what's going on here, again, with night blindness, what happens is the rods are actually the ones that are not functioning. Now, which ones help us with color? It's the cones. And so rods aren't necessarily helping us with the color, but they are helping us with general shapes. And so if there's something going wrong with the rods, we're really going to see things fuzzy. And if you have night blindness, that's going to make it even harder to see in the dark. Sometimes when you that's why, like, if you have night blindness, they don't let you often drive at night, or they tell you shouldn't drive at night. Now, color blindness, this is where our notes end, but after this, there's a few videos that I want you to watch about color blindness, and it's going to explain it, honestly, a lot better than I could. And but what I do want you to know is when somebody says they're colorblind, in most cases, that does not mean that they see everything in black and white. People say dogs are colorblind, and so they think dogs can only see in black and white. That is not true. If somebody's colorblind, that doesn't necessarily mean that they're only going to see in black and white. That does happen rarely, but that's what's known as monochromatic color blindness. And what happens there is pretty much you don't have any of your cones for vision. Again, the video is going to talk about how we have red, green, and blue cones. And these cones are what help us when they blend together to decipher colors. If we're missing one of those cones, then we're lacking some information. We can't figure out things. And so that's what leads to seeing colors incorrectly, you could say. And then last but not least, glaucoma. Now, some of you guys might have seen commercials for this before. Maybe your grandparents have had it. Maybe you know somebody else who has had it, but haven't really understood what's going on. All right, and what happens with glaucoma is, remember those humors that we talked about that keep your eyeball at the correct shape? Well, if you have too much of that vitreous humor sometimes pressing in on your retina, eventually it's going to start to destroy that retina. And so that's what's going to lead to that blindness. It's that increased pressure on the eye, pushing down on the retina, and it's going to actually destroy those rods and cones. And so that's how glaucoma leads to blindness. So right now, that's it for our notes today. What I want you to do is go ahead and I want you to watch these 3 videos. So again, the links for these videos are in the descriptions. This first one is just going to really explain how colorblindness works. Again, what's going on in this picture, you can make out some colors right here, and he's going to explain this, but this is basically what a dog sees. Still color, but not as vivid, you could say, as the colors that you see over here. And he's going to show different types of color blindness, and I want you to look at the 2 images. He's going to have images on each side like this, and I want you to think, do they look different? And if they don't look different to you, well, you might just have that type of color blindness. And then after that, again, remember what light is. It's just certain wavelengths, and so certain wavelengths will produce certain colors. Understanding that, we can produce glasses that can start to basically help with that, where it knows, okay, this person does not have the cone for depicting, let's say, green light. And so these glasses kind of help change those light waves before they get to the person, so they can see what true green might look like. And so this video, I just always enjoy looking at these videos because this is science in action right here. This is showing you, why are we learning all this? Because it can actually be used to help people see the world like never before. And then last but not least, we do have one person who is monochromatic. In other words, this person is absolutely colorblind. He sees the world in black and white. But he has considered himself to be a true cyborg. You can see this little thing right here. And what he's going to be talking about is how he doesn't see color, he hears it. And so that's actually going to lead us also into what we're going to be talking about tomorrow with hearing. So again, watch these videos. Tell me what you thought about the videos in the comments. If you have any questions about what we talked about today, put that in the comments. And I'll talk to you guys later.